Okay, so I'm Stephen, and I'm doing my talk on gravitational lensing. So, we're going to start with just a basic overview of what gravitational lensing is. We're then going to move on to a little bit of physics, and I'm just going to caveat it there. I'm not an expert, I'm not a physicist, so I apologize if I butcher it. Then we're going to move on to some of the pretty pictures of gravitational lensing, and then we'll talk about some of the uses of gravitational lensing. So, what is gravitational lensing? Gravitational lensing is it's an effect predicted in general relativity. It's when light is bent by large masses in space. It is also a very effective tool for learning more about the universe. So, foundation physics. Energy and mass they're two sides of the same coin. Mass is energy it's not moving. So, we're going to consider, if you've got a light beam and you're traveling next to it, and if you can travel at the same speed of light, you can look over, relative to you, it's not moving. But if it's not moving, then it must be mass, because mass is energy that's not moving. So, can light, so relative to you, can light ever stop moving? This is sort of what Einstein was tackling, and his conclusion is that, one of his conclusions is that no, compared to you, light is always going to be moving at the same speed. So, the result of this sort of thought experiment is that time, if I'm traveling and at close to the speed of light, the only way for light to keep moving is for time to slow down. So if you consider, if you have two people, one of them is stationary and one of them is moving really close to the speed of light, and the one who's moving releases two beams of light, and one beam hits a speed sensor of the guy standing still, and the other one hits the light beam that's traveling with the person. If they're both going to register the same speed, how is that possible? The answer is that the time for the fast-moving person is slowed down, so the same distance over that slower time produces the same speed. This might seem far off and crazy, but they've actually observed it in particle accelerators, where they accelerate muon particles to close to relativistic speeds, and they actually see that the half-life grows. So, if time isn't constant, well, why should we assume that space is constant? When Einstein was working with trying to figure out his equations of general relativity, he saw that the equations for Euclidean space just weren't working, and that they actually looked a lot more like the equations for curved surfaces. And when he replaced the equations for Euclidean space with curved space, his equations began to work. So from this, so space can be curved. It's not this flat, boring concept that most people think it is. Also, there's an underlying constant that ties space and time together. It's called space-time, and it is consistent throughout the universe. So, now, what does this mean for gravity and light? Now, if you have a person who's in a box, and there's no gravity whatsoever, then they're going to take an object, they're going to let it go, it's just going to sit there. They're going to take a laser pointer, across your box, it's just going to go straight, and it's just going to sit there. Now, if you, or this person in their box, is in free fall, they're going to take something out, they're going to let it go. It's also not going to move anywhere. Again, you take your laser pointer and you shine it across the room. You're not going to be able to tell that you're falling, which Einstein took this and said, well, if you can't tell that you're being affected by gravity, then it's as if you're not being affected by gravity, and so the rules must be the same. So, now, going to our laser in a box. If the box is falling, and I shoot my laser, it's going to go right across the wall. And I'm not going to be able to tell, I can't tell that I'm falling. But if you observe from outside, from the point that you initiated the beam of light to the point where the beam of light hits the wall, in order for, within the box, for the observation to make sense and to follow this rule, the light actually has to bend. So from this, essentially what it means is that gravity can affect the path of light. So, what does all this physics stuff mean? What it means is that mass can affect the path of light, which means, and because space and time are no longer flat, they're curved, the shortest path between any 2 points is no longer a straight line, and there's no longer even just a single path that is the shortest. So, some of the effects of gravitational lensing. You get things that are called multiple images, things called Einstein rings, and you can get magnification. The first gravitational lens was in 1919. A group by Sir Arthur Eddington went out during an eclipse, and based on the predictions of Einstein, expected that the star that could be seen just past the sun was going to be bent. And it was the Hades star cluster, and it was, and they confirmed that gravitational lensing does occur. So now to the pretty pictures. What you see here, this is 2 quasars. So, or it's 1 quasar, and so this is things that have the shiny beams off them. Those are the quasars. And then you see here, there's another circle. That circle in the middle is a galaxy. And the 2 images of the quasar are actually